we had considered several interesting properties of the Laplace transformation in the last two lectures. So, it is a good time now to work out a number of examples which illustrate the application of these properties. First example, let us find the Laplace transform of a function f of t which is represented graphically in this form. This is t in seconds, f of t has a value of 4 units at t equals 2 seconds. So, this is the function f of t whose Laplace transform we are required to find. So, we can express this f of t as from this point to this point it climbs by an amount of 4 units in 2 seconds. Therefore, the slope is 2 units, it is a ramp function, it is 0 for negative values of time. Therefore, 2 r t. This describes the behavior from 0 to 2. At this point, instead of climbing up at a rate of 2 units per second, it is climbing down at the rate of 2 units per second, because in 2 seconds it comes down by 4 units. Therefore, the net slope must be minus 2. Therefore, you must bring this positive slope of 2 units to a negative slope of 2 units. Therefore, you must introduce a negative ramp of 4 units, and then that ramp is introduced at t equals 2 seconds. Therefore, this minus 4 r t minus 2. So, if these two ramps alone were operating, then this continues to go down like this, but at this point the downward slope must be arrested, a net slope of minus 2 must be arrested, and then it will be flattened out. Therefore, to introduce another slope of plus 2 units at r at t equals 4. So, it is these 3 ramp functions which describe this characteristic. Therefore, we can find f of s as 2 upon s squared minus 4 upon s squared would be the Laplace transformation if it has been 4 r t, but since this is delayed by 2 units, you must introduce e to the power of minus 2 s. And this has a ramp of 2 units, therefore, 2 over s squared is a basic Laplace transform of the ramp function, but since it is delayed by 4 seconds, you must introduce e to the power of minus 4 s. So, that would be the Laplace transformation of this. It is illustrative to obtain the same result by differentiating this f of t maybe once or twice and finding out the Laplace transform of the derivative functions, and then go back and see how it agrees with this or not. So, let us see. If I take the derivative of this f prime t, then for 0 to 2 seconds it has plus 2 units slope of plus 2, and from 2 to 4 seconds it is a slope of minus 2. So, that would be the derivative function 2 and minus 2, that is the derivative function, that is f prime t. Now, if I take the second derivative of this, once again take the derivative of this, you have here, we are thinking of this is 0, therefore, this is also 0. Therefore, there is an impulse of 2 units here, 0 to 2, 2 units impulse, and at this point it jumps from plus 2 to minus 2. Therefore, there is a negative impulse of 4 units, therefore, minus 4 is the strength of the impulse. At this point again it climbs up by 2 units, therefore, this will be 2. So, you can write f double prime t, that is the second derivative of the function of time f double prime t, as 2 delta t minus 4 delta t minus 2, because that is an impulse standing at t equals 2 seconds, plus another impulse function of 2 units at t equals 4. This is the second derivative of this. The second derivative now consists purely impulse function, therefore, its Laplace transform is easy to find out. So, Laplace transform of the second derivative is delta t has a Laplace transform 1. So, it is 2 minus 4 delayed impulse minus e to the minus 4 e to the power of minus 2s, and this is again a delta function, therefore, this is 2, and but it is a delayed impulse, therefore, you must introduce a term e power minus 4s. So, that is the Laplace transform of the second derivative. To find the Laplace transform of the first derivative, that is, this is obtained by integrating this. So, if you know the Laplace transform of this function, the integral will have the same Laplace transform divided by s. Therefore, this will be having the Laplace transform 2 upon s minus 4 upon s e to the power of minus 2s plus 2 times e to the power of minus 4s over s. In addition, normally you have the integral value of this function at t equals 0 minus, in this case it is 0, therefore, that does not appear here. Now, once we have the Laplace transform of this, the Laplace transform of its integral, that is the Laplace transform of this, is obtained by multiplying this by 1 over s once again, and that is what you are having here. So, this also illustrates that the possibility that when you want to find Laplace transforms of functions like this, you may find them directly, but alternately you can take the derivatives and find if the derivatives Laplace transforms are easily found out, then you can use that information to find out the Laplace transform of the original function. There are two alternative approaches. It also illustrates the rule for integration that we have already discussed. Let us take a second example. A. Find the Laplace transform of t cubed e to the power of minus a t ut. And after having found that out, evaluate zero to infinity of t cubed e to the power of minus a t dt. This is the question that is asked for us. Now, to find this out, we can, let us say, method 1. We start with Laplace transform of t. We know t ut, that is 1 over a squared. T squared ut is minus d by ds of 1 over a squared, because this is multiplied by t. Multiplication in the by t in the time domain corresponds to the negative of the derivative in the s domain. So, minus d by ds of 1 over a squared, which of course is 2 upon s cubed. Then likewise, you can carry this one more step. T cubed ut will be, you once again have to take the derivative of this. This will become 3 factorial by s to the power of 4. That is t cubed ut. But now, if f of t has a Laplace transform f of s, f of t multiplied by e to the power of minus a t, the Laplace transform of that is obtained by substituting s plus a for s. This is something which we have already discussed. Therefore, t cubed ut multiplied by e to the power of minus a t, its Laplace transform is obtained by substituting s plus a for s. So, this will be 3 factorial or 6 over s plus a to the power of 4. This is, that is what it is. Now, let us do this by taking another approach, method 2. Let me start with the Laplace transform of e to the power of minus a t u t. So, e to the power of minus a t u t has the Laplace transform 1 over s plus a. Now, t multiplied by e to the power of minus a t u t is once again minus d by ds 1 over s plus a, that will be 1 over s plus a whole square. Then likewise t square e to the power of minus a t u t, that will give me by the same process, taking this second derivative, again the derivative of this with respect to s and putting a negative sign, it becomes 2 over s plus a whole cube, and t cubed e to the power of minus a t u t will fetch me 2 times 3 factorial over s plus a to the power of 4. So, that is the same result that we obtained earlier. So, this problem we worked this out taking 2 different approaches, starting with the Laplace transform of t cubed u t first, or Laplace transform e to the power of minus a t at first. As I said, these are 2 alternative ways of doing this. Now, for the second question, now let g of t be t cubed e to the power of minus a t u t. It has got the Laplace transform, let us say g of s, which is this, right. Now, if I take the integral from 0 minus to t of g t dt, you can say 0 because after all there is no it, yeah, the 0 plus value of g of t is also going to be 0, therefore, whether you take 0 minus or 0 plus makes no difference. So, I simply write 0 to t of g t dt. This has got the Laplace transform g s upon s, because the initial value of the integral is taken to be 0, therefore, it is g s upon s. Now, what is 0 to infinity of g of, suppose this is h t or some, what we want is not 0 to t, but 0 to infinity. Therefore, 0 to infinity of g of t dt can be regarded as the final value limit as t tending to infinity of h of t. So, the final value of this function we want to find out. This function has got this Laplace transform g s over s. To find out the final value of this function, this is equal to limit as s tends to 0 of s times g of s over s. That is the final value theorem. To find, if you know particular function has a Laplace transform g s over s or whatever it is, h of s if it is, if you like, then the final value of h of t, h infinity, is obtained by taking the limit as s goes to 0 of s times h of s. Now, in this case s times g of s over s. So, this is indeed s cancels out g of 0. So, the final value of the integral from 0 to t of g t dt, it happens to be simply g of 0, where g of s is the Laplace transform of this quantity. In our case, g of s is equal to this, therefore, the final value, that means when s is equal to 0, this is 3 factorial 6 upon a to the power of. So, that is the answer for the second part, 6 upon a to the power of 4. In other words, what we are having is, the principle that we are using here is, if f of t has a Laplace transform f of s, what we are saying is 0 to infinity of f of t dt is equal to f 0. That is what the principle that we have used here. This is quite easy to see why it is so, because after all f of s equals 0 to infinity of f of t e to the power of minus s t dt. When you substitute s equals 0 in this becomes f of 0, and this is 0 to infinity of f of t dt, because this becomes 1. When s is equal to 0, this becomes 1, and that is the same thing that we have used here. So, all these are tied up in some fashion or other, but what we wanted to do here is to illustrate the rule for integration, and then they also want to illustrate the application of the final value theorem in working out this solution. As a third example, let us consider the convolution of a function of time with a delta function or a unit step function. So, using Laplace transforms, find what these functions amount to. F of t convolved with delta t first, b f of t convolved with u of t. If you recall, the results we already know. When we talked about the convolution property in the introductory lectures, we said whenever a function is convolved with delta t, that function is reproduces itself. That means f of t star delta t is f of t itself, because the delta t scans this function as it moves along, and at any particular point the value of the product of delta t and that f of t, the displaced delta t and f of t will be f of the value of the function at that particular point of time, that is the magnitude of the impulse, and when you integrate, that will be f of tau times f of tau whatever it is, wherever it is situated. Therefore, the convolution of this will be must result in f of t itself. And when we talked about the integration rule under Fourier transforms, you recall that f of t convolved with u of t has been shown to be the integral of f of t. We will see these results here in the using Laplace transforms. So, A, we know that the Laplace transform of f of t convolved with delta t is the product of the Laplace transforms of the two individual functions. This is f of s multiplied by 1. The Laplace transform of delta t is 1, therefore, this is f of s. And the inverse Laplace transform of f of s is equal to f of t. Therefore, f of t star delta t is f of t itself. That is what we already know. Second question, f of t convolved with u of t has for its Laplace transform f of s multiplied by 1 by s. So, this is f of s over s, and we know that f of s over s has the inverse Laplace transform 0 minus to t of f of t dt. So, when you convolve f of t with a unit step function, it is the integration of f t. In the Fourier transform theory, we might have taken this from minus infinity onwards, but in the Laplace transformation, because we are dealing with causal time functions, we take the limit from 0 minus to t, because f of t is assumed to be 0 for negative values of time. That is the difference. So, the integral of f of t dt from 0 to t is f of s over s, and that is indeed the product of the Laplace transforms of these two functions. Therefore, we conclude that f of t star u t is 0 to t of f u du if you wish, because after all this is a dummy variable, the integral of f of t, assuming that f of t is a causal time function, and therefore, we are starting the limit, the integration from 0 minus onwards. These results are already known, but this is only a confirmation of results that we already derived in an earlier context. Example 4. Let us consider now a section of a circuit in which we have an inductance L of 1 Henry and a capacitor of 1 farad, and let the voltages across the two elements be described as V c and V L. In some circuit analysis, we have obtained V c, the Laplace transform of V c of t, the Laplace transform of the voltage across the capacitor is found out to be A s plus b over s squared plus C s plus t. Through some analysis, we have obtained this. Using this information, we are asked to find V c 0 plus the voltage of the capacitor immediately after 0, the current in the circuit at 0 plus, this is the current I t, and the voltage across the inductance at 0 plus. These are the three quantities that are required to be found out, right. Now, since we are interested in finding out the 0 plus values in all these situations, we can assume that the Laplace transform that we are talking about, f of the Laplace transform defining integral, start from 0 plus 0 onwards, not from 0 minus, because we are after all interested in 0 plus values. That means, we ignore any jumps in these functions from 0 minus to 0 plus. We assume that all our functions starting from 0 itself, and therefore, we can use the 0 plus value instead of 0 minus value wherever it is necessary. So, let us see V c 0 plus, the initial value of the capacitor voltage is limit as s goes to infinity of s times V c of s. That is the initial value theorem. Therefore, this will be limit as s goes to infinity of A s plus b upon say s square plus C s plus d multiplied by s. This must be multiplied by s and take the limit as s goes to infinity. Therefore, that will be A s squared plus b s over s squared plus C s plus d. And when you take the limit as s goes to infinity, as I mentioned in the last lecture, we can take s going to infinity in the along the real axis in the positive time axis. Therefore, we can this ratio of the two leading coefficients only, because all the other terms pale into insignificance. C s plus d pales into insignificance with s squared, b s becomes negligibly small compared with A s squared. Therefore, it is the ratio of the two leading coefficients. Therefore, this is given. So, the immediately after 0, the capacitor voltage at 0 plus, as you approach 0 from the positive direction, will have a value A. Now, what about the current? We know that the capacitance I equals C dV C dt. That is the relation between the current in a capacitor and the voltage across the capacitor for any general variables I t and V c. Therefore, I equals C dV C dt. Therefore, we can say the Laplace transform of the current I f s is C times, if V c has the Laplace transform V c of s, the derivative dV c by dt is s times V c of s minus. Now, we are taking stock of all values from starting from 0 onwards, 0 plus onwards. Therefore, I may write here V c 0 plus. If we are starting all our accounting from 0 minus, you would have put it at 0 minus. That means, I am trying to take the value variation of current. Suppose this is a variation of current, I am taking the stock from 0 plus onwards only. I am not considering the jump from, if any, from here to here. Okay? Right. That means, if there is any jump in V c, suppose V c 0 minus is this and V c 0 plus is this, the current would have an impulse here. But those impulses I am ignoring. I am talking about the variation of the current I for t greater than or equal to 0 plus. Only that is the type of current which I am interested in. So, that is why I am putting V c 0 plus. So, this will be C in our case is 1 farad. So, this will be S times V c of S. V c of S is A s squared plus A s plus B over S squared plus C s plus D. Therefore, S times V c of S is A s squared plus B s over C s squared plus C s plus D minus V c 0 plus has been just been evaluated, that is A. Therefore, when you do this, then it becomes B minus A c times S minus A d divided by S squared plus C s plus D. That is the Laplace transform of the current IFS. To find out I 0 plus, we apply the initial value theorem and say that this is equal to limit as S goes to infinity of S times IFS, which means limit as S goes to infinity of B minus AC S squared minus AD times S divided by S squared plus CS plus D, which by the same arguments as before is the ratio of the two leading coefficients, which will be B minus AC. So, this is the answer for this. So, the initial value of the current is B minus AC amperes, if this is the Laplace transform of the voltage across the capacitor. Now, again, to find out the value, initial value of the voltage across the inductor VL equals L di dt. In our case, the inductance value L is 1 Henry, therefore, this is di upon dt, which now tells us that VL of S is S times IFS minus I 0 plus. Once again, we are taking the variation of the voltage across the inductance from t equals 0 plus onwards. We are ignoring any changes from 0 minus to 0 plus values. So, we again multiply the expression for the Laplace transform of IT, which is this one, multiply this by S, substitute and remove from that I 0 minus, which is B minus AC. If you do that, I will not go into the details of this. This will turn out to be, I will give some expression here, and then VL infinity is limit as S goes to, I am sorry, VL 0 plus, that is what we are interested in, limit as S goes to infinity of S times VL of S. So, after carrying out this work and take this limit as S goes to infinity of S times VL of S, you will get the answer minus AD minus BC plus AC squared. So, that so many volts is the value of the voltage across the inductor. This example shows that once we have the Laplace transform of some quantity and to find out the initial values of different quantities associated with this capacitor voltage in this case, we really did not have to carry out the numerically the value of the capacitor voltage VCT at all, and symbolically in terms of ABCD we are able to evaluate this. So, in other words, if these are particularly unwieldy numbers, say 97, 35, 9.5, whatever it is, you do not have to do the numerical work, try to find out VL of t and from that VC of t and then try to find out I of t and then from that VL of t and then find the initial values of these respective quantities. You can straight away use the initial value theorem and get all the initial values of the quantities which you are interested in.